All right, so this person's pushing this, whoa, pushing it that way. That's a clockwise direction, which I think they told us. Clockwise, you're pushing would be a negative. Clockwise is negative, counterclockwise is positive. After the push is ended, does the ball's angular velocity? If you're applying a force, wouldn't the angular velocity, what would it do? Oh, sorry, it says after the push has ended. My bad. After it is ended. So if there's no force, there's no acceleration, and if there's no acceleration, it's going to hold steady. I suppose it would help if I read the question correctly. Explain the reason. No force slash torque in this case, because it's rotating, equals no acceleration. And in this case would be no angular acceleration. Right after the push is ended, is the torque positive, negative, or zero? We just said there's no torque, so there's no torque equals zero. There's no torque, so it's zero. Sorry. All right, let's see what they gave us here. Whoa, why do I always do that? So we have torque up here, we have acceleration there, and we have angular velocity there. They give us a moment of inertia, so we have torque of 20. We need acceleration. So don't we have an equation that looks something like this? If I rearrange, actually, no, I need acceleration. So the torque would be on top, and it's 20. Where did I get that from? Right there. Newtons times meters the unit. And my moment of inertia is 10. kg times m squared. This would equal 2 radians per second squared. So I need some sort of So I need to go up to 2. I'm going to go 1 and 2 right there, and I'm going to say that the acceleration was 2 for the first 2 seconds. Now I'm going to look at part 2. There was 0 torque. 0 torque equals 0 acceleration. And now I have negative 10. So acceleration equals torque over moment of inertia. Torque was negative 10. Newton times meter. And my moment of inertia is still 10. That equals negative 1. Negative 1 would be there. So from 4 to 6 seconds, I would have negative 1. Now, going backwards is going to be kind of weird. It said it started at 0. I need a slope of 2, because remember, I'm going the opposite way now. I need a slope of 2. So for 2 seconds, if you were increasing by 2 every second, you'd be up to 4. So I need to at least get up to 4 here. So if you think about it, 1 second would be there. If I start at 0 and I'm accelerating at 2 radians per second every 1 second, I'd be at 2. And at 2 seconds, I'd be at 4. So this line has to have a slope of 2 because of my 2 up there. Then I have 0. So I'm going to be there's no torque. It's just going to continue on at what it was. And now I'm going to slow down. I need to have a slope of 1 for 4 seconds. So I'm at 4. I need to drop to 0 in 4 seconds. And it should look something like that. I need a negative slope of 1. So I'm at 4. Then I'm at 5, 6, 7, 5, 6. At 5 seconds, I'm dropping 1. At 6 seconds, I'm dropping another 1. And back to 0. Woo-woo. Woo-woo. So this one's kind of fun. It's on a frictionless axle. It's wrapped around a smaller diameter. The block is released and hits the ground at t equals 1 second. So basically, you have to decide where your ending velocity is going to be, and a constant force will give you a constant acceleration, or a steady increase of velocity. And then after that, after it hits the ground, it should just stop, right? I suppose that would keep spinning when the wheel keeps spinning, but the block would stop. So if the string ran out, the block or the wheel would keep spinning after the block hits the ground. Is the magnitude of the block's downward acceleration greater than, less than, or equal to g? Is it in a free fall? No, so it can't be greater. Nothing's being applied on it. This wheel is inhibiting it from being in a free fall. It's got a string. Free fall would just be if you dropped it without anything, so it has to be less than g. Why? Because it's not in a free fall. The wheel inhibits it. Wheel inhibits the fall. The moment of inertia of a uniform rod is, we did one in class with that. The moment of inertia is 1/3. Explain why the moment of inertia is larger about the end, about the center. Well, 1/12 is going to make this smaller. So around it smaller, it'd be easier to push. The one around the end is bigger. 1/12 is smaller than 1/3. And if you think about it, the rod around the end axis, so one of them is rotating here. That one is 1/3. The one that rotates around its center is 1/12. This one is small. This one is big in moment of inertia. The reason for the rod around the end axis equaling bigger, more mass is further from the axis of rotation. If you really want to read into that, it has a larger radius. Larger radius equals larger moment of inertia. You have more mass further away from the center. Remember we said on the merry-go-round, if the mass is towards the center, it's easier to push. If the mass is way out here, away from the axis of rotation, it's going to be harder to push. Hope that helps. Bye-bye. All right. Radius doubles on one of them. Volume is pretty much equal to radius to the third power. So when we double that to the third power, this is 8 times greater. Because volume is length times width times height. That's where I got that from. So it's 8 times bigger. 8 times bigger equals 8 times the mass. So our moment of inertia equals mr squared for most objects. We just said the mass goes up by 8 times, so that would be 8 kilograms. The radius, didn't we say doubled way back here, twice the radius, so the radius is 2. It went from 1 to 2, I doubled it, but it's r squared. So 2 squared is 4, 4 times 8 equals 32 times larger for doubling the radius. Because both the mass goes up and the volume goes up, or the radius, I should say. The radius goes up. But because of the squared and the 3 times, it goes up a lot. 32 times bigger. Hope that helps. Bye-bye. All right, if I look up the moment of inertia for a solid sphere, you would find the I equals 2/5 mr squared. If you look up the hollow, you will find that the I equals 2/3 mr squared. Everything is the same. The mass is the same, the radius is the same between the two. The only difference is 2/5 versus 2/3. 2/5 is smaller, is less than 2/3. So if it has a larger moment of inertia, which this hollow does, the hollow sphere is harder to rotate. Remember, we said it's just like mass, it's harder to push. Or if you want to look at it the other way, the solid sphere is easier to rotate. However you want to look at it, is easier. Now, careful here, these are same mass, same radius. Is easier to rotate. Because, why is that? Because more in the solid sphere, I'm going to change color here. Solid sphere equals more mass closer to center. That's a huge deal. It's a big deal. Kind of like me. All right, this one's a little confusing because they keep using R when that's the total length. And then they give us masses. So what we really have to do is look at both sides. So let's look at I of 1. The I of 1. All right, I1 equals mr squared. Well, I have two masses. And this is the confusing part. The radius is not the r, it's half of that. But the radius gets squared. So that's going to turn into 2m r squared over 4. I have a 2 on top and a 4 on the bottom. That goes away. That turns to a 2. This is going to equal 1mr squared over 2, which we would probably just write as 1/2 mr squared. All right, let's do I2. I2 we're going to have to separate into 2 because I have different masses. So on one side, it's, oops, let me back up a smidge here. There we go. All right, we have 2m times r squared, but it's half r. So this is really crazy. It's half of r half, which is r to a quarter, but it's squared. I hope that makes sense. If I cut a half in half, I have a quarter, so it's 1/4, but it's squared. And then I have to add that to the second side. Now I'm on this side. I have 1m, and again, I have a quarter of a radius because half of a half is a quarter. So what's this going to turn into? This is 2m r squared over 16 plus mr squared over 16. This is going to turn into, isn't this 1/8 mr squared, because it's 2 over 16. This is 1/16 mr squared. And if I remember elementary school, 1/8 is 2/16 mr squared plus 1/16 mr squared, which turns into 3/16 mr squared. Boy, that was fun with a capital PH. All right, let's do the last one. We have to do this side, then we have to do this side. So I equals, let's do the first one. It's mr squared. I have half of an m. These are getting weird, aren't they? And my r is 2r, so 1r is r squared. Now let's add that to the other side, which would be exactly the same. I have half an m and half of 2r, which is 1r, but I have to square it. And this is basically 1/2 m and 1/2 m here, which equals m, and I have an r squared. 1/2 mr squared and 1/2 mr squared equals 1 mr squared. So just to review, this is getting crazy. I1 was 1/2 mr squared. Squared. I2 was 3/16 mr squared. And I3 we just did was mr squared. Wasn't I supposed to rank them in order or something? From largest to smallest. So the largest would be I3 is greater than, what's larger, 1/2 or 3/16? 1/2 is larger. And the smallest one is I2. Boy, that was a lot of work, wasn't it? Really why I picked this page, because the solid disk has a smaller I, rotational inertia, the hollow, didn't they say hollow? Circular hoop. So the hoop has a larger I/rotational inertia. Why? Because, same mass, same radius. That was the big deal here. It has a larger rotational inertia. Why? Because more mass is further from center. So if you have a small rotational inertia and the same force, which I'm on a ramp or something like that, right? Down to the bottom of a ramp. So same force / torque in this case, because it's rotating. Small mass / rotational inertia. I missed that word somehow, didn't I? Small mass, which we're not calling mass anymore, it's rotational inertia. Why am I missing on that? Rotational inertia. It's going to be easier to move / accelerate faster, or accelerate more, I should say. So the hoop, or the solid disk, sorry, I'm getting my shapes all mixed up. The disk, which is the solid, which I called up top, the disk, this is disk. The disk, which is solid, which has more mass towards the center, will go faster, and it will reach the bottom first. This is one I want to talk about Monday in class. Reach bottom first. It has more get up and go because of the smaller mass / rotational inertia, which we're now calling I. Woo woo, woo woo.